So now we're going to look at some other approaches to estimating EFA that allow us to incorporate a little bit more theory. They're a little bit more flexible than the principal component solution that we saw in the last set of slides. So the principal component solution is the most data-driven approach. It's based on the principal components analysis. So it is really sort of to an extent letting the data do the talking in a similar way, with the main difference being you're flipping around the perspective, so you're only interpreting a certain number of the components, treating them as factors, and you can then do some rotation, which makes them a little bit more interpretable. There are some other methods for estimating the communality, which is what we're really interested in exploratory factor analysis, that don't rely strictly on the principal components. And so while these are still data-driven, they tend to be more flexible, especially when you have some kind of theoretical expectation. So one common alternative is called the principal factor solution. This is also called the principal axis solution. In R, it's typically called the principal axis solution. In the book, it's called the principal factor solution. The way it works is we're going to start by assuming we're working off of a correlation matrix, not a covariance matrix, so that all of the diagonal elements are ones. Another way to think of this is that we're trying to get at these h-squared values, which are our communalities. And just I mentioned this in the last set of slides, just as a reminder, we could think of these as the r-squared between variable I regressed on the other p-1 variables. And so we're trying to estimate this h-squared from the correlation matrix as the component of, as the communality component of the ones on the diagonal of the correlation matrix. So to do this, we're going to replace the diagonal elements of our correlation matrix with these communalities. And this will give us a reduced matrix, which we're going to call R sub R. We're then going to use this reduced R sub R matrix to extract our M eigenvector pairs, just like we would in the principal component solution, but now we're doing it based on this reduced correlation matrix. And that'll give us our factor loadings. And we can then proceed to do everything the same way that we've done with the principal component solution, just based on this reduced correlation matrix. So there are different methods for estimating the principal factor solution. The one that R uses is based on an iterative algorithm. So we know that the specific factors psi represent information about the variances of the original data, or in the correlation matrix, these are just the uniqueness components of the ones on the diagonal. So the h-squareds are the communality components, and the elements of psi are the uniqueness components. And together they're going to sum to one, which is the diagonal elements of the correlation matrix. They don't factor into the covariances or the correlations. Those are strictly based on the communality. So therefore, if we could just estimate psi, we could get our L transpose L, or L transpose matrix, our loadings matrix, our communality matrix, just by subtracting psi from the correlation matrix, which also means that we can get our communality estimates as 1 minus the uniqueness estimates. So the iterative solution proposes that we start with some sort of starting values for psi. And so these are usually going to be based on the inverse correlation matrix of the data. So we're going to use the 1 over the the diagonal of the inverse correlation matrix, just as our starting values. Then we're going to find an initial principal factor solution by using these values to get our communalities. And we're going to create our reduced correlation matrix, and we're going to get our factor loadings for L based on that reduced matrix. And then we're going to go one step further, and we're going to replace the diagonal of the reduced correlation matrix with our new communality values based on the principal factor solution here. And we'll call these h-squared star. And this gives us another new reduced correlation matrix, R star R. And then we're going to check how different our communality estimate is between our initial estimate from just based on our starting values, and then the new communality values based on our estimates from the reduced correlation matrix. And we're going to see how much that changes the overall communality. And once we're going to keep repeating this process over and over again replacing the communalities with the new communalities until the difference is small enough that we stop. So in the example that we've been looking at from the Wechsler Adult Intelligence Test, at the time there was quite a bit of debate as to whether there should be a 2-factor or 3-factor solution to the model. These data actually only have subtests for 2 of the factors, the verbal comprehension and perceptual organization subtests. So this provides us with a theoretical expectation. And that means it's more appropriate to use something like the principal factor solution because it's more flexible in how it constrains the communality components. So the next few slides show my code for computing the principal factor solution based on this iterative algorithm that I just described. This is how the psych package works. This is how it computes the principal factor or principal access solution. You don't have to know how to do this necessarily, but the code just might help you sort of understand what's going on. I know going through it helped me sort of wrap my head around exactly what the iterative algorithm is doing. So here I just walk through it. So first I compute the inverse correlation matrix, get the diagonal elements, and initialize them as psi. And then I obtain my reduced correlation matrix as R minus psi. Then I'm going to use a while loop. So this might be new for some of you if you've never seen a while loop. What it does is it keeps looping through different iterations of the loop until a certain condition is met. So in this case, it's going to keep going through the loop, and then it's going to check whether the difference between the old and new communalities are still above 0.001. And if they are, it's going to go through it again. Once they are less than 0.001, it's going to stop. And so I'm also going to track the number of iterations just so I know how many times it goes through the loop. So then inside the loop, I'm just going to repeat this process where I get the first 2 eigenvalues and eigenvectors, which is m, because I'm specifying m equals 2 of the reduced correlation matrix to get my factor loadings. Then I'm going to replace the diagonal of my reduced correlation matrix with the sums of each element of the eigenvalue eigenvector pairs to get my new R star reduced. And then I'm going to check the difference between the diagonal, the sum of the diagonal, or the trace of R, and the trace of R star R. And if it's small enough, it'll stop. If it's not small enough, it'll keep going through the loop. So this is the while loop. And so I'm starting out by initializing my iterations and error just so I can get the loop going. I don't need to do the iterations. This is just so I can count how many iterations it's going through. And then I run my loop. And so now I can save the final factor loadings based on the final 2 eigenvalue eigenvector pairs of the final R star R. And so here we see these are my final estimates for the factor loadings. And we see that it went through 8 iterations. So the loop went through 8 times before the difference got small enough that it stopped. And we'll see that these almost perfectly match what the psych package is going to give us. For some reason, this first one is like off in the very slightly off in the 4th decimal. So I'm assuming that's just a rounding error somewhere, but the rest all round off to be the same values. So this is really what the psych package is doing for the principal factor solution. Just like with principal components analysis, we could start with a Scree plot here. Even though we have a good theoretical expectation, it's always good to check the data isn't kind of like wildly diverging from our expectations. However, when the results are not based on the principal component solution, the plot is going to be a little bit different, and it's not going to use the eigenvalues of the data itself. It's going to use the covariance matrix of the data. It's going to use the eigenvalues of the communality matrix. And so by default, it's going to use the 1-factor solution for the communality matrix. And this is in simulation and empirical studies has been shown, although it underestimates the communality a bit, it tends to be better than overestimating. So you can increase the number of factors for the communality matrix here, but it's not necessarily recommended. I do it here, but you don't really typically have to do it. And if you use too many, then especially with parallel analysis, it could kind of break the simulation. So all of the factor analysis based functions in the psych package have some common arguments. So FM is the factor method. So here we're going to use PA for principal axis, which is the same as principal factor. N factor is the number of factors to estimate. So this always defaults to 1. Rotate is the rotation method to use. And then the FA parallel function also asks you to whether you want to do EFA or PCA for the parallel analysis, or you can specify both. This is the FA equals argument. So you can specify it as PC, FA, or both. So here I'm going to do FA. So this is my Scree plot based on the principal axis or principal factor method with factor analysis, not principal components analysis. So this is based on the communality matrix of the factor solution. And I'm using 2 factors. Usually you can just ignore this argument and leave it as 1, but here I'm just using 2 because I know that I'm expecting 2, and that's what everything's been based on so far. So this principal factor solution definitely suggests there's at least 2 large eigenvalues larger than the simulated parallel analysis, and maybe even a third. The third one is sort of borderline. I mean, the rest of them are sort of borderline. They're pretty much right along this line. So let's check the factor loadings. So the unrotated factor loadings will match what I got before. So we can see that this all matches up with the results of the algorithm that I ran. That matches what I got. Now let's use the rotated solutions. So this will increase interpretability. So here I'm using the Vera max rotation. And so what we see here is that we get a very similar pattern to what we saw before. So the first 4, the first factor loads on the first 4 variables, the second factor on the last 4. Here's the 3-factor solution. And so this is getting a little bit more muddled now. And it's kind of similar to what we got with the principal component solution, but even arrangement is not super highly loaded by the 3rd factor here. So another approach to estimating an orthogonal factor model is the maximum likelihood approach. So assuming that both the common factors f and specific factors epsilon are normally distributed, we can do we can use maximum likelihood. So that's sort of the assumption here. So without getting into too much detail about the math, which will be to some extent in your book and probably in your lecture notes, we can specify a likelihood function, which gives us the probability of the observed data given specific parameters. And essentially what maximum likelihood is doing is it's scanning across the different parameter values to figure out which ones maximize this likelihood. So which ones produce the highest probability of the data given those parameters. So in the psych package for maximum likelihood, we specify the FM equals FM argument equals ML. So here's a Scree plot. We can see it's pretty similar to what we got before. It's a little bit different than what we saw. And here I'm just using the 1-factor solution. I'm not using 2. It really doesn't matter too much here. The results are the same. And this is just the 1-factor solution for the communality matrix, which again is going to underestimate the communality a bit, but that's okay. It's still estimating that there's 2 eigenvalues of that communality matrix that are larger than the parallel analysis. So we can then go and get our factor loadings and check them again. So these are very similar to what we've seen. The estimates aren't exactly the same as the principal factor solution, but the pattern is very similar and the estimates are close. These, however, are very different. So I'm not sure why it reorders the column names here, but the pattern's the same. For the first 2 are pretty similar in that we get high loadings on the first 4 variables, then high loadings on the next 3 here. But now the last one is really being driven by objects. This is a very different estimate of the 3-factor solution than what we got with the principal factor solution. And so when the principal factor and maximum likelihood solutions sort of disagree like this, it can be interpreted as evidence that this factor structure isn't being reliably estimated very well. We should probably avoid it. So this is one way of determining that a factor solution probably is not one that you want to go after for your data. So a third approach, and this is I'm going to cover this because it's the default in the psych package, is called minimum residual. In practice, it's very similar to maximum likelihood. It's actually based on ordinary least squares rather than maximum likelihood. And it's trying to minimize the residual between the model implied and the observed covariance matrix. So here's the Scree plot. So I don't need to specify anything for the FM argument because this is the default. So here I'm going to get the 2 and 3 factor solutions again. And so here we see these are, once again, the 2 factor solution is pretty consistent with what we've seen so far. And this 3 factor solution is similar to the maximum likelihood solution we got, and similarly different from the principal factor solution that we got. In general, if you're confident that your data are going to fit an approximate normal distribution, maximum likelihood is going to usually perform just as well as the minimum residual approach, and then offer some other advantages that we'll talk about in the next set of slides. The minimum residual approach is going to be a bit more flexible in cases where you are violating these assumptions, or you have a matrix that is not what they call behaving very well. So the minimum residual approach is going to probably give you be more likely to give you stable estimates in cases where you have kind of unusual data. And you could use the minimum residual there instead. And in cases where the data is normally distributed, it's going to perform very similar to maximum likelihood. The difference is that it does have some disadvantages in terms of what we're going to look at next when we start thinking about kind of test statistics and stuff like that. These are both generally preferred at this point to the principal factor solution, but the principal factor solution sort of has a lot of historical importance, and it's still used to some extent, so it's worth understanding as well.